Hi, I'm Charlie Nobles, Executive Director of the American Sailing Association. Welcome to our video companion to ASA's 105 level course, Coastal Navigation and Piloting. We created this video especially for this course to demonstrate the key skills you'll need to master to become a capable navigator. I hope you'll find this video helpful and that you'll refer back to it if you get stuck working through any of the problems in the course book. Probably the greatest thing about working for the American Sailing Association is having the opportunity to meet and work with some of the best, most experienced sailors in the world. You're about to meet one of these remarkable sailors, ASA instructor Captain Tom Tersey. Captain Tom holds his U.S. Coast Guard Ocean Master's License and has been teaching ASA courses from basic keelboat through offshore passage making for 15 years. More important, Tom has sailed over 50,000 miles and crossed all the world's oceans. So let me introduce you to Captain Tom, who will show you how to navigate with confidence. Thanks for watching.
Hello. In this course, we'll teach the basics of navigating by paper and pencil methods. Even in this age of modern electronics, it's essential to understand the basics of paper and pencil navigation because it forms the foundation of everything else that we do. Think about driving your car. When you drive your car, you navigate by looking at familiar objects around you. You look at the street signs, building numbers, intersecting street numbers. You look at the hardware store in the corner. By the way, turn right at the hardware store, go down 2 blocks to the greenhouse on the left with the red shutters. And this is the way we do it ashore. But when we're out at sea, familiar objects are few and far between. We have great distances and it's water everywhere. You might see the marina entrance at some distance from you, but you don't know how far it is and you don't know what direction it is from where you're located. So we need different techniques. We can use paper and pencil techniques to do that and draw on those charts in order to figure our distances and directions. There's also electronics, modern electronics, for example, GPS, satellite navigation. There's electronic chart plotters. There are electronic range finders. There are night vision scopes that can be used. And all of these things are very valuable aids, but if you do not understand the fundamentals of navigation that underlie them, then their use is going to be very ineffective. So learning basic paper and pencil techniques of navigation is going to enable you to sail to new locations by doing proper planning before you go. Foul weather sailing, where you have limited visibility, rain or fog, if you have to make route changes for changes in weather or personal injury or mechanical breakdown, you're going to be able to plan those route changes much more effectively. Hazard avoidance, there can be coral rocks below, but also it's going to give you increased confidence in what you do, where you sail, and therefore it's going to increase your enjoyment. It's going to enable you to make better decisions because those decisions will be based on knowledge. They're going to be informed decisions. Now, the primary tools that we use for this paper and pencil navigation are very simple. First off, we have the navigational charts themselves. These are the paper maps that show land features and other information that we're going to use. This first chart that I have here spans the entire Atlantic Ocean. Here's the east coast of the United States, here's the west coast of Africa and Europe, and here is the ocean across. And this covers a distance of about 3,000 miles. Over here you can see Cape Cod, a little projection there on this chart, and as you see, it's shown very small in this chart. This is called a small scale chart because the objects on the chart are small. This next chart shows the Western Atlantic and the East Coast of the United States. It's a larger scale chart. That is, the objects on this chart are larger. So here now we look at Cape Cod. It's a much larger image. The next chart I have in line here is even larger scale, and it shows again Cape Cod in a very, very large image. And the next chart shows Cape Cod in very large image. This is a larger scale. This would be a harbor chart to enable us to navigate within this Cape Cod area. So in the case of the very first chart that I showed you, in the ocean chart, that was a scale about 1 to 6 million. In other words, 1 inch on the chart represented 6 million inches on the surface of the Earth. This last chart, the harbor navigation chart that I'm showing you, is a scale of 1 to 20,000. Now, the additional tools that we use are reference books, and we'll talk about those in greater detail later. There's plotting tools, and the plotting tools, there are many to choose from, and every day someone invents a different plotting tool. But there are a couple that I find very effective for use on a small boat at sea. The first is a parallel rule. And the parallel rule is 2 straight edges that are attached together. And as you see, I can move them, and these 2 edges stay parallel to each other as they're moved. So if I take a chart and I want to draw one line parallel to another line, I can use the parallel rule for that purpose. So let me draw first here a line. I have a vertical line on the chart. And now I want to transfer that line to some other location and make sure that the second line is parallel to the first. I take the parallel rule and I line it up with that first line. I move the other rule and I can draw another line. And I now have 2 lines that are parallel to one another. And this is used extensively in our chart navigation, paper and pencil techniques. The next item that we have is a protractor triangle, which can be used for measuring angles. You could measure the angle of an existing line, or secondly, you can draw a line of a certain angle as you desire. I will just arbitrarily draw a line in here, and then the question is, fine, what's the angle of that line? In order to do that, I'm going to take the triangle protractor and my parallel rules, and I'm going to align the edge of the protractor, the triangle, with this line that I want to measure. Then my next step is to slide the protractor along the parallel rules until the crosshairs join up with the vertical line. At that point, I come down here and I read the degrees of that line, and as you can see, it's 120 degrees. I can move that a little bit. It's 120 degrees. The second use of this triangle protractor is to draw a line of a particular angle. So if I decide that I want to draw a line, let's say 55 degrees, well, what I'm going to do then is line up this part of the scale on 55 and line up the crosshairs here on the vertical line. Might have to make a couple of moves to do that, but I want to end up with the crosshairs on the line and 55 on the line. I then have this edge of the triangle is at 55 degrees, and I can move it to wherever I want using a parallel rule, and I can then draw a line, and that line will be at 55 degrees. And remember, this one was at 120. The next device that we use, the next tool that we use, is a dividers or a calipers, which has on one side a needle point, and on the other leg it has a pencil point. And it has an adjustable screw in the middle. And I can adjust this screw to change the distance between these 2 points. And I can use this for a couple of purposes. One purpose is that I can use it to measure the distance between 2 points. I take one point of this dividers and put it on the first point. I adjust the screw until I get to the second point, and I now have between these 2 points the distance between those points on the paper. I can then take it and put it on a scale, a measuring scale, which I'll show you later, and actually get a number for what that distance is. The other way that I can use this divider is to draw an arc, since it has a pencil on one side. And if I need to draw an arc, I can put the needle point down, so I put it on that point, and I can now draw an arc. We also have to use compasses, and there are 2 types of compasses that we use. One is the boat's steering compass, which is attached to the boat, and when you're steering the boat you look at that and take readings over it. Secondly is a handheld compass, which can be used to sight and measure the angle, the magnetic direction to a particular object. I can sight through the crosshairs on this and sight over the compass and get a number as a result. So that's a handheld compass. In addition to those items, we have instruments on the boat which are speed and direction measuring instruments. We have a clock or a watch, wristwatch, to measure time, depth sounder to measure water depths, VHF radio to talk to other boats and to land facilities. We have binoculars to have a better image of distant objects. And we have instruments for measuring wind direction and speed. So those are the primary instruments for doing navigation by paper and pencil techniques. In order to make measurements of location, distances, routes, and so forth on the surface of the Earth, the different nations of the Earth came up with an agreement on setting up an arbitrary grid that we superimpose on the Earth. That reference grid is centered on the axis of rotation of the Earth. And I know that all of you are familiar with this from your grammar school geography, but let's go through and review it briefly just to get on the same page. Here's a globe of the Earth, and as you know, the Earth rotates on its axis, which goes through the North Pole and the South Pole. That axis, the axis of rotation, forms the basic orientation of the grid that we draw on the surface of the Earth. Halfway around the Earth from the poles is the equator, and this goes around the Earth at the center part, halfway between the 2 poles. Now, we have arbitrarily drawn a set of circles that we call lines of latitude. They're also called parallels. These lines are drawn parallel to the equator. That is the line of 0° latitude, the equator. The North Pole is referred to as 90 degrees north. That is latitude 90 degrees north. And between the two, we have various lines of latitude as you come from the equator to the pole. And as you see, as we go from equator to pole, these circles or parallels become smaller in diameter, but they're all parallel to one another. The second part of the grid that we have are the vertical lines that go at right angles to the equator, And these vertical lines all pass through the poles. And the longitudes are actually centered, begin at Greenwich, England. Greenwich, England is 0 degrees longitude. So running through Greenwich, England is a vertical line, a vertical circle, going all the way around the Earth. And this half of it is referred to as 0 degree longitude. On the other side of the Earth, the other half of that circle is referred to as 180 degrees longitude. And as I go from Greenwich, England, towards the United States, that is westerly, those longitude lines are then designated as westerly longitude. So I'll go from 10 degrees west, 20 degrees west, and so forth, all the way up to 180 degrees west. I also go from that Greenwich longitude east, and I get to 0 to 180 degrees east longitude. Then we take this grid that's on a spherical globe and we put it onto a flat paper chart. It has to be stretched and distorted. If we look at a set of these lines, we'll see that at the equator, they're very widely spaced, and as we get closer to the pole, they become closer and closer together. So they converge as you go towards the pole. Paper charts use a projection method called Mercator projection. And there's various projection methods, but Mercator is the one that's most commonly used in marine navigation. So what the Mercator projection does is it takes this grid from the Earth and stretches it out so that the further you get from the equator towards the pole, the more stretch there is in that surface, so that eventually you put it out flat. The result of that is that the longitude lines, where on the globe they converged, on the flat paper chart, they're parallel now to one another. And the objects are actually stretched. So Greenland is bigger on a flat paper Mercator chart than it is on the globe itself. The benefit of that is that we're able to draw